going to talk about hydrology, and what I would like to do is to make these presentations as brief as possible in terms of what I have to say, but I want you to pause and follow the instructions. You're going to be watching other videos in between this presentation, so I want to encourage you to do that. So we're going to talk now about hydrology. As I mentioned, definition, hydrologic cycle, watershed, precipitation, abstractions, and runoff. We're just going to talk a little bit about runoff in this video. In the part 2, we'll do the actual hydrographs and unit hydrographs. So, hydrology from the Greek means water, and logos, study. So it's the study of water, how the water moves and is distributed around the earth, including the water cycle, water resources, and environmental watershed sustainability. It's the science that encompasses the occurrence, distribution, movement, and properties of the waters on earth, and the relationship with the environment within each phase of the hydrologic cycle. We'll talk about the water cycle, but basically all the water in the world that has been here is here. So we go through the process of evaporation, the clouds condense, and then precipitation, and then you have water. Part of the water goes underground, but other water stays on the surface. So this is an endless cycle that allows for life to occur here on Earth. There's two main branches of hydrology: surface water hydrology and groundwater hydrology. This specific module, Module 3, deals with surface water hydrology. The fourth module will deal with groundwater hydrology. So what I want you to do is to pause this video or this PowerPoint presentation, which is also available on Blackboard. See the description of the water cycle in your textbook, and then click here to watch the video. One important thing is that all of the videos that are embedded in this presentation, you will find a quiz on Blackboard. So go ahead and watch that video that describes the water cycle. The next video that you need to watch has to do with what is a watershed, and this is a super important definition, and I found a video that can explain it better than I can. Again, after you watch this video, make sure that you complete a quiz that is on Blackboard. You can go directly to the quiz if you want to just watch the video one time and then just do the quiz as well. The next video you will find is on how to delineate a watershed, and this is super important because your short project, group project, you will have to delineate a watershed here in El Paso. So watch this video carefully, and also you will find another quiz. From the videos, you'll probably have found that rainfall data is really important, and rainfall data can be found in different sources on a daily basis, hourly, every 15 minutes, continuously, and usually it's reported as depth, which is really volume over a given area over a period of time. So 1 inch, 2 inches, 3 inches, and then they can talk about volume as acre feet, as you probably also saw in the field trip that you had the opportunity to go to. So the U.S. National Weather Service and the USGS, they have a lot of information about weather, but really it's the National Weather Service that collects this precipitation information. The USGS just repeats the same information. So if you want to find all of this information, go to the National Weather Service data, and you can see that here we are in the El Paso area, about 8 inches. This, I'm not sure what year was this, but it varies anywhere from 8 to 9 inches per year. These are some of the links that you can find. I encourage you to look at those and play with that data. And I want to talk about what's a hyetograph. A hyetograph is something very important because it's a graphical representation of the relationship between rainfall intensity and time. You saw that in the lab. I hope you'll remember. I think it was the first lab that you had to calculate rainfall intensity. So whenever you talk about rainfall intensity, we use capital I. So it's usually the depth divided by time, whether it's inches per hour or millimeters per hour. It's how intense the rain is. So it's inches per hour. So if you have a high intensity, that means you have high depth in a short amount of time. Whenever we talk about a hyetograph, it's the plot of rainfall intensity drawn on the ordinate axis. So it's intensity and the ordinate axis, and then time here in the abscissa. So it's a bar diagram. So whenever you have a hyetograph, you will see how a storm, and I want you to be very observant. I hope there will be a storm before the end of the semester. But you see how whenever you find that it starts to rain, the storm starts very low intensity. And then there's a point in which the intensity is at its peak. And it's usually right in the middle of the storm. And after it reaches that peak, the intensity is reduced. So if we look at intervals of time, we look at interval time, the intensity is of a certain magnitude, and then it goes something like this, and then it'll reduce. So it has this kind of shape, almost a normal distribution, but it's a skewed, more like a T-student distribution. So this is really important in predicting storms that we'll use for design of hydraulic structures and to predict extreme floods. So what I have here is the incremental, and it's this here is represented. Let me delete this so you can observe the others. So what happens is that if you look at the characteristics of storms, you will find this distribution, which is incremental if we were to use just a graph instead of a bar chart. And then if we start looking at the accumulation, the actual accumulation with time, then it's a graph that reaches a plateau. And this is the incremental, and really this is the hyetograph that we'll be using. Okay? So in a hyetograph, what you're looking is at a specific site, and if you had a rain gauge, you measure how this rain gauge is changing with time to measure the rainfall intensity. And as soon as there's a prediction for rain, I'll let you know. So this could be one of your labs that you can do in your house. So as I said, this is a plot of rainfall intensity versus time, and often assume that the intensity remains constant within a fixed time interval, which is what we're saying here. Within this time interval, we're saying that it remains constant. So you see this figure, and this is what I just said. So you have the intensity in centimeters per hour or inches per hour, and then the time in hour. We can present the accumulation, and so whenever we talk about accumulation, the symbols here are very, very important. So for intensity, we used I. Of course, time is T. And then when you say P is the accumulative or cumulative precipitation. Okay? We could present a dimensionless curve as well, where you have to divide the precipitation divided by the total amount and the T over the total duration of the storm. So TD is the storm duration. Okay. It's important that you complement all these lectures with what is in the book. These are very straightforward concepts, and I want you to read carefully through the book. We're in chapter 11 of your textbook. So these are examples of calculations for a storm hyetograph. So you're checking at different times what is the intensity, or if you're checking precipitation, then you have to divide the precipitation by the interval of time. And then you have your change in precipitation, and if you have here 0 and 0.3, this is the point here, and this is your difference in time, and this is P over PT. So the total precipitation is PT, so PT is total precipitation. Okay. And basically, I mean, and it depends on how you present it. I hope there will be some information on some storm that we'll have, and I'll let you know. So be aware that I might call on you last minute whenever there's a report of a storm coming, so you can do one of the labs at home. So there are actual storms and there are design storms. So whenever we prepare a hyetograph from an actual storm, what you're doing is measuring the actual precipitation with time. So you would have a rain gauge outside of your house, for example, and you measure the precipitation at different stages of the storm, and you see how that precipitation is changing with time, so that you'll be measuring probably the total precipitation as it goes with time, and then you have to calculate the intensity based on this delta P divided by your interval in time. So this would be your intensity for that interval of time. But there are also design storms, and the design storm comes from the term of a design event. A design event is what is used for the design of a hydraulic structure. In other words, you don't design a structure for the storm that's taking place today, but for a more extreme storm, so that the hydraulic structure will function properly at full capacity. The design storm that is used depends on the risk of failure that is allowed, meaning that if I have a dam that is upstream from a city, I have to make sure that I design for a more extreme design event than if it's just a dam that is protecting agricultural fields and not really a lot of people. So you always have to think of protecting human life, and that's the most important thing, and that's where you have to allow for the lowest risk of failure. So then we're going to be talking about design storms. The design storm is the precipitation pattern defined for use in the design of hydrologic system. And this is what you're going to use for a design of a hydrologic system. So let's just define what is a design storm. So you probably have heard how people talk about, oh, this was a 100-year storm, or a 500-year storm, or a 600-year storm. That's the average recurrence interval. But that really has two interpretations. So, for example, if you have a 100-year storm, that means that the probability of occurrence in a given year is 1 in 100. So if it's a 500, it's 1 in 500 for a given year. So that means, this is the same as a 1% chance of happening. or if it's a 1 in 500, there's a 0.2% chance of happening. So that's why whenever we get 500-year storms, it's like, wow, that's unheard of. This is not supposed to occur very often. But, once in a while it does happen, like in El Paso. So this is really, really important to remember, because the different design structures are designed to either a 50-year storm or a 100-year storm or a 500-year storm. Now, tied to that recurrence interval is the duration of the storm as well. So, for example, here, a 100-year, 24-hour rainfall storm. So it's tied to the duration. So this is a 100-year storm, meaning that it's a storm that will happen, has the probability of occurring in a year at 1%. And this is the duration of 24 hours. So for 24 hours, it's going to be raining. So this is, remember that these are design storms. So you kind of foresee a type of extreme event that could happen. So a 100-year, 24-hour duration storm is a kind of an extreme event. And so some structures are designed for 100-year, 24-hour storms. So it's not just a 100-year, it's the duration of the storm. Another way to describe is a 24-hour rainfall depth that has 1 in 100 chance of being met or exceeded each year. So I hope that this helps. And remember, the good thing about the video is that you can pause, and the PowerPoint is also available on Blackboard, so you can be looking at the PowerPoint as well. So this design storm information, where can you find it? And I'm going to give you a lot of different sources, but just keep in mind that even though it's different sources, the root source is the same. So it's just that different people have made it available in their websites because it's their mandate by some legislature that tells them, you are also to protect, or help in the design of hydraulic structures. Or, for example, TxDOT, will provide that information for design, because you have to use their manuals for design of highways and bridges and all of that. So what they have done, rather than have you track down the information to the original source, they just repeat that information in their handouts or in their website. So don't be overwhelmed if I mention a lot of different sources, because in the end it's the same information. So it's not that each source has different information. Okay, so that's very important. Now what can happen is that if you are going to work in a specific city or town, that town will add some specific intensities or durations of storms for their design, and they give you additional information that is more strict than the federal information that you can find from like NOAA or other sources. Okay, so one of the original sources of information is called a TP40. That's the U.S. Weather Bureau technical paper number 40, and it's a lot of that information. It's still valid. So it's in 1961. So there's a lot of movements that say, it's time to change that, because yesterday's 50-year storm is today's 100-year storm. So that has to be revised, and some states have made some efforts to add some more design constraints, so that some of the structures, instead of revising this TP40, what they have done is, if a structure before had a design storm of 10 years, 24-hour duration storm, they said, okay, now we're going to design for 50-year. Okay, so they really, what they have done is, instead of changing the probability of occurrences, they just have increased the type of extreme event for which the structure is designed. Okay, so these are some of those sources. Feel free to pause and look at those sources. And the sources can be found in different ways. You can find them as graphs, you can find it as tables, you can find them as equations. So each source can have the information presented differently. So that's really important to recognize. Here you have a 2-year 60-minute precipitation, and it's given in inches. Sometimes you can find the information for intensity. What would be the intensity of such storm, for example? Okay, so this is a 100-year, 24-hour rainfall, and you can see here we are. So that doesn't seem like, it would be very strict anymore, right? Also, the USGS has a lot of publications on depth, duration, frequency. They have it for many states, like for Texas, and you can find FEMA also has depth, duration, frequency storms, and so they have for El Paso and for Texas in general, and they tell you what are the locations for those predictions. So here you have, for example, a 100-year, 1-hour storm, 2-hour storm, 3-hour, and of course here we have the 24-hour storm. Okay, so you can find this manual from TxDOT that they use, and I'm not sure if this is still valid, but you can Google it and find another similar source, and these are just examples. This is not specifically what we will use in class. In class, we'll use values that are applicable to El Paso only. So that if you move to another city, then each city will have its own requirements. So the design storm selection, as I said, it's what you use for hydraulic structures. And when I say hydraulic structures, you probably saw the first video in Blackboard, and it talks about ponds, conveyance structures, dams, and all of those are hydraulic structures that whose purpose is to protect human life and property from excess runoff, and to control and constrain, like in the case of a pond. So this design storm selection depends on the importance of the structure, the cost, the level of protection, and the consequences of its failure. And this is where I'm saying, the consequence is human life. Well, then you have to have a very sturdy structure. In Blackboard, in your resources sections for manuals, you will have the El Paso Drainage Manual and the construction standards. And I believe that there's a TxDOT for highways. If not, it's easily found online. The El Paso Drainage Manual and the construction manual, you should be able to find it online. But what I have found is that the drainage manual is not totally complete, what you find online. So what you will have in your Blackboard is the complete manual, okay? These are copies of those manuals. So whenever you're going to design a structure in El Paso, you're going to refer to these two, the Drainage Design Manual and Design Standards for Construction. It will tell you everything you need to know to design your hydraulic structure in El Paso. If you move to another place, then you have to check on their engineering department, and sometimes they combine engineering and planning, and look for, ask for drainage design manual or design standards for construction. If you are outside of city limits, if you are a good engineer, you will follow city codes for your design, because not all the counties have their own drainage design manuals or standards. So these are examples of what you find in the drainage manual and construction manual, how to design park ponds in the city of El Paso. So it should retain a 24-hour, 100-year return storm. Okay, so that means that that storm has to retain all of that volume that would be accumulated, that would result from a storm that has a duration of 24 hours and that has a 10% annual exceedance probability. Okay, so this is the probability. So let me go back to that slide to review some of these terms. So this is the average recurrence interval, or you can just call it the recurrence interval, the probability of occurrence, and then the percent chance of occurring in a given year is the probability of recurrence, right? So whenever we go to the manual, so then you have the annual exceedance probability, which is the probability of recurrence in a specific year, of occurrence in a year. Okay, so here I say see handout, but I will be showing you. So what I want you to do is to look at this question and look at other slides and know that this is a 10-year, 24-hour for Illinois in that case. So you have to look for the 10-year, 24-hour rainfall, and sometimes other sources are better resolution, have better resolution, like here is the National Weather Service. So as I said, you know, all the sources have the same information. So if it's just over 4 inches here, 4.1 would be conservative. So now remember the hyetograph. It's the time distribution of rainfall. So what you're looking at a hyetograph is intensity and time. And as I mentioned, you measure that intensity and you measure the time. But another thing that you saw is that the intensity depends on the duration of the storm. Okay. Well, for a specific storm or specific duration, first of all, what you have is this. So whenever you look at the intensity and the time, depending on what time you are measuring the intensity, the depth is the intensity, right? So you have the highest intensity sort of like in the middle of the storm. And this is for a storm that has a specific duration. But then that intensity also depends on the duration of the storm. So this is some intensity depth curves, intensity depth frequency curves. So here is the duration of the storm and then the return period. So that if you have, for example, a storm that has a duration of 70 minutes versus the storm with the same recurrence, this is for, and it happens for all of them, what you see is that the longer duration of the storm, the lower the intensity. It goes in this direction. So the intensity is higher for shorter duration storms. And this is a very important aspect that needs to be remembered, because whenever you're doing engineering work and get some numbers that should not be happening, that's one of the first things you do. You look at a duration of a storm, and then it was a higher intensity as you increase duration, so you're doing a wrong calculation, right? So the other thing that I want you to look is how also the intensity increases with the return period of the storm. So a 1 year, 10 year, 20 year, or 50 year, this is more intense. So those two things are key features in all IDF curves that you will find, intensity depth frequency curves. That's how they are called. Okay? So those are the two things that we noticed. So how do we use the drainage design manual? So I'm just going to give you an example. So in the drainage manual, there are two things that you need to look for. Which side of town you are in. So you'll find these maps here, and then, for example, this is the west side, so this is just 2 pages, right? So you'll see the west side, duration, depth, frequency, okay? So it gives you here the depth, and you have 1 to 500, 1 hour, 2 hour, just like FEMA does, okay? But then the intensity equations are here, and you have to use them depending on the duration of the storm. So we'll do some examples later on about this. I just want to show you that because many major cities have these different guidelines to look for your IDF curves, and they apply some specific ones to their city in different regions. Okay? So what I want you to do is to look at this drainage manual, because the units are super important. Make sure that I will give you the equation, but you need to know which units to use. Is it duration in minutes or hours? Okay? So that then what are the intensity? And the manual tells you that. It's just that it's not on this page, it's at the end of these equations. But you will see all that information. Okay? So this part I'm just mentioning because if we had the time, if this was face-to-face, I would mention it. But what I want you to remember is that we will not go into a lot of detail, but if you want to be challenged and love or learn to love hydrology, then maybe you will want to do it. But so as I mentioned earlier, you measure the intensity with time for hyetographs, but sometimes you don't have that information, so you need to generate a synthetic hyetograph or a storm hyetograph or a hyetograph for a design storm, which is what we're going to talk about, because that would not be available. You have to determine it. Now there's software that does that for you, so I just want to go through this real quick, but I just want you to know that there is a methodology for creating design storm hyetographs, not the actual storms that we saw at the beginning of this video, but design storms. And for the reason I'm showing you this is because it provides you with some valuable information about the types of rainfall distributions in the U.S. Okay, so the Soil Conservation Service is what used to be called NRCS. So now it's the Soil Conservation Service under the USDA that is in charge of all of this information. So, and as I said, we're not going to really go into the complete development of the storm hyetograph, but there's some information that it's valuable. So according to the Soil Conservation Service, there are these 4 types of rainfall distributions throughout the United States. And one of the things you notice is that most of the U.S. is type 2, okay? But then we have here these darker areas. This is type 1. This is type 1A, and this is type 3. What does that mean? Okay? Well, what does that means is the type of rainfall distribution. So type 2, let's go over that. So type 1 and 1A is wet winters and dry summers, 1 and 1A. So 1 and 1A is Pacific maritime climate with wet winters and dry summers. Then 1A is the least intense, and this is the one that I never forget, because when you're like in Seattle or Oregon on the coast, it rains a lot, but it's not very intense. You're just feeling like, someone is constantly spitting on you, because it's very low intensity, okay? So this is what it tells the 1A, that is the least intense. And then type 2 is the most intense, short duration. So this is the rest, and we can see that in El Paso, right? Where you don't have long duration storms. They are very short duration, but very intense, okay? And then type 3, which represents the Gulf of Mexico and Atlantic coastal areas where you have a lot of rainfall, okay? So basically, this figure here is representing, this is time, and then the P over PT, remember that you can have a hyetograph with dimensionless units where P is the rainfall depth and PT is the total rainfall depth. So this kind of like shows that pattern for each one of those storms. So those are synthetic patterns of rainstorms in those 4 areas. And those same patterns are then represented in these figures. So what this does is it gives you a dimensionless pattern of rain. So if I multiply this by, let's say that I tell you now, let's say if you have a 6-inch rain, then you have P over PT, and you multiply the 6 inches, and you will get the actual precipitation or intensity that you'll get for that specific storm. I hope that is clear. So what you have is these values that are here for each one of those types. If you want to see what would be the actual rainfall distribution, how many inches of water I would have in the Pacific Northwest if I have a total precipitation of X, then these numbers you multiply times that to obtain that rainfall distribution. So I hope that is clear. And then this is a 24-hour distribution, so that's why it goes from 0 to 24. It's a 24-hour duration rainstorm. So there's hundreds of these tables that show, well, not really hundreds, I mean maybe dozens of tables, because they have these tables, they have developed these tables for different duration storms so that you can develop a design storm hyetograph, okay? So this is an example of what I said. It's determine the precipitation. So I'm not going to go over everything, but then if it's a type 2, which was the coastal, then what you do is you have your type 2 distribution, and then you have to multiply, as I said, the precipitation for each one of those would be that, okay, from the table. And I lost that, but basically what I did was draw that. We're not going to go into details, but now you know how to use those, okay? So I can provide those 2 Excel files. If you like being challenged, develop hyetograph for Central El Paso for a 10-year 24-hour storm or a 500-year 24-hour storm. Okay, so now let's talk about runoff, and you have seen a little bit of runoff in your slides. If rainfall rate exceeds the soil infiltration capacity, ponding begins, and any soil surface roughness creates storage on the surface. So whenever you have all the depressions that have accumulated the water that they're going to trap, runoff begins. If additional runoff continues and exceeds the saturation of the soil and all that, then you have runoff. So it's just running water. So you have rainfall, and anything that stops rainfall from turning into runoff are abstractions. We call them losses from the rainfall because they don't show as stormwater runoff. So we have interception, evaporation, evapotranspiration, storage, surface infiltration. You saw that in the water cycle video. So runoff is also called effective rain, rainfall excess, or excess precipitation by other names. So in watersheds, you also saw what is a watershed. So in a watershed, you can have a hyetograph from a storm event. And depending on the characteristics of the basin, then is the resulting runoff, which is the hydrograph. So the hydrograph tells you the runoff. And this is very important because the hydrograph does not include all of the rainfall that's falling on that watershed, because it's as if I had a gauge at the exit of that watershed, and this is what I would be measuring. So if I have an actual storm, then I measure this outlet coming out of the watershed, and that is the flow rate that I'm measuring resulting from that storm. If I have a design storm, I can develop a synthetic hyetograph and then a synthetic hydrograph, right? If I have all the information, and that's what modelers do to model the storm runoff. And there's different softwares to do that. And HMS is one of those. HMS. So the basic characteristics that you need to know are the size, topography, length of streams per area, vegetation type and distribution, geology, soil type and thickness, and then of course the runoff processes. So these are actual events. So there was a rainstorm event, and there's going to be a delay, okay? So you don't see the hydrograph right there and then, okay? And the total rainfall event is not necessarily going to be the total hydrograph or the total runoff